So hello everyone. In today's lecture, I would like to combine the method discrete event simulation with a simplified production process. So we are going to produce products, and those products are sent to the customer. For that, we need a shop floor. So we are going to discuss the functionality of a shop floor. We are applying the method discrete event simulation. I'm just going to activate the laser pointer. We calculate some basic key figures like average inventory, average WIP, average finished goods inventory, utilization, lead times, processing times. Then we are also going to discuss random variables. They are predefined in our example. And then we are going to simulate this one machine model. We have two steps. We have step 1, the internal logistic parameters, and step 2, that we include the customer side FGI inventory, service level, and tardiness. Step 2 is reserved as an assignment. So you can do it at home and you can compare the solutions. So next step, next slide. Here you can see our process. So we have a source generating customer orders. Whenever this machine is idle, the next order can enter the machine. When the machine is producing, then the following orders have to wait in the queue, because only one order per time is allowed to enter the machine. And after the processing is finished, the items are delivered again to the customer. So for an example, it could be that somebody is ordering a car. Immediately after the customer order, the production starts. When the car is assembled, the customer can take this beautiful car. Or it can be more service orientated. The customer enters a McDonald's restaurant, orders a Big Mac. The customer has to wait until the Big Mac is produced for him, until he has to wait until it's produced, and then the customer can take the Big Mac and can leave McDonald's restaurants. So you can see that the inter-arrival times for the orders are different. So the first order arrives at time 0 because the inter-arrival time, which is the time between two customer orders, is 0. The next order, order A1, arrives at time 0 plus 6.77, because this is the time between the two orders. Order A2 arrives at time 0 plus 6.77 plus 2.18, and so on. And you can immediately see that the inter-arrival time changes between the orders. So we have a stochastic system. So not every, for example, 5 time units a customer arrives. It is different. So in the beginning, immediately a customer orders appear. Then we have to wait 6.77 time units. Then we have just to wait 2.18. And the next customer arrives after 3.04. And as well, you can see the same behavior for the service time, for the processing time at the machine. So the first order needs 4.91 time units to be processed. The second order needs 2.55 time units. The third order, 3.02, and so on. And here again see that we have predefined stochastic values for the service time. And this makes the planning more complicated because we do not know how long the processing time will take, because it's stochastic. So in this case, of course, we are not going to determine this example in group work. So I'm going to present immediately the results. So what we are going to do, or I'm going to do, is that I develop a chart for the scheduling over time, that I'm going to introduce a chart for the queuing time, or for the queue over time. And based on those two charts, I'm going to calculate the key figures, average utilization, the inventory of the queue, the lead time, and the corresponding maximum and minimum values for the inventory and the lead time. And of course, I'm also going to provide the list of the events happening in our simulation. So then let's get started. What happens first is at time 0, the first order arrives because the interarrival time is set to 0. Due to the fact that the inventory of the queue is 0, the order passes immediately through the machine and increases utilization. So the utilization pops up from 0 to 100%. And now this order is processed 4.91 time units. That means the next event happening is at time 4.91. And the event which takes place is order 0 is ready. And we get for free the first lead time of this order, which is just a processing time of 4.91 time units. And we can see here, this is just the processing time. So we don't have any queuing time, which increases the lead time. At time 6.77, order 1 arrives in the system because the interarrival time is 6.77. So here we have a period where nothing is being produced. So the utilization at that point in time goes down to 0. And we don't have any inventory in the queue because no orders are arriving. Next event which takes place is time 8.95. Here order A2 arrives, which is calculated by 0 plus 6.77 plus 2.18. And we can recognize that this order 2 has to wait in the inventory of the queue because we are still producing the previous order. At 9.32, the processing of the previous order is ready. And that is as well the time where the order 2 can go immediately into the machine. And we also get the lead time for order 1, which is 2.55, which again is just the service time or processing time, because we don't have any queuing time for this order 1. So we can see again here, this is the utilization here is caused by order 0. This utilization part is caused by order 1. And now we start to produce order 2. And what you can see here, again, this is the first time where a waiting time in the inventory is generated because order 2 is not able to move into the machine because it's occupied by order 1. Next event happened at time 11.99, calculated by summing up the interarrival times 0 plus 6.77 plus 2.18 plus 3.04. Here in this circumstance, again, order 3 arrives. Recognize is that machine is occupied and order 3 has to wait in the queue and the inventory increases to 1. So what we can see here is we can see that, as I explained already, for order 0 and 1, the lead time is just the processing time. But for order 2, we can see that also a waiting time is included. So we have to sum up the waiting time here plus the processing time equals the lead time of A2. That means if we generate queuing time, then the lead time increases and will be greater than the service or processing time. Here you can of course see already the waiting time for order 3, because this order 3 is now released to the machine. We can see that the next order arrives at 14.24 time units. And again, an order arrives at 14.76. Unfortunately, no more orders are ready up to time 15, because our simulation time or time of observation is up to time 15. So within this time frame, only 3 orders are completed. Order 3 is not completed because it's being processed in the machine. But now we can stop our simulation, our manual simulation, and calculate the key figures. The inventory is calculated by summing up all the areas divided by the simulation time. Or in other words, it's the integral of this graph divided by the simulation time. And then you recognize the average inventory is 0.115. The same goes with the utilization. You sum up the area of this chart and divide it by the simulation time. Or you take the integral of this graph and divide it by the simulation time of 15 time units. Then you identify utilization of 87.6%. The average lead time is the average of those 3 orders. And the drawback is that only 3 orders are processed, so we can only take 3 orders into consideration for calculating the average lead time, because the 4th and the 5th order are just in the queue and are not ready with the processing itself. A nice thing here is if you do a discrete event simulation, even it's just manually, that we can identify the minimum and maximum values for our inventory and for our lead time. Assume that we would like to identify how many products should be stored in front of the machine. So we would like to identify the maximum queue length in front of the machine. So we will have a look on this inventory of the queue, and then we recognized that the maximum is 2. So we can set or assume to the production planner, logistics planner, supply chain planner that the inventory should be at least 2 units. If you would take the inventory, the average values, you would have problems when the inventory goes to 1 or to 2, because this would not then be allowed. And if this would not be allowed, orders cannot be accepted, and the customer gets unsatisfied because he does not get the product when he has ordered the product. The same goes for the lead time. So the maximum lead time is 4.91 and the minimum lead time is 2.55. And we can see differences in the statistics. We have continuous elements and we have discrete elements, statistic elements. Yeah, so discrete element and discrete example of a discrete element is the lead time. So the time itself does not influence the result of the average lead time, because it does not change the result if we know for 10 seconds that A0 has a lead time for 4.91 or if we know it for 10 minutes, for example. So the lead time is not depending on the time. However, for continuous elements, such as the average inventory, very much depends on the time. So this means for continuous elements, we have to know the value itself when the value changes. So at that point, the inventory increases to 1. So we need to know the point in time where the change happens, and we need to know the amount of the inventory. And then we are able to calculate the integral of this curve. The same goes for the utilization for the machine scheduling chart. So we need to know when the utilization changes, and we need to know from which value to which value the utilization changes. So we have two different types: statistic elements, continuous elements, and discrete elements. So for homework, we are not going, or I'm not going to judge this homework, but you will get most likely a manual simulation for your exam. So I highly recommend that you calculate step 2 by yourself. What we are going to introduce here is an FGI inventory, so which is the finished goods inventory. That means orders or products which are finished in production are waiting in the FGI inventory until the due date of the customer has been reached. And then the customer is satisfied and the products leave the FGI. So for that, you need the due date. So for example, for order 0, the customer wants to have the item at time 0. For order 1, the customer requests the item to be ready at time 10. So again, you have to determine the following chart and key metrics up to time period 15. So I request you to draw the chart for the FGI inventory, so for this queue here, and you calculate the service level and the average lead time of the FGI. So I think the average lead time is straightforward, so because you have just to measure how long an order is waiting in this queue. And the service level is a new key metrics and is defined by the orders which are leaving the system on time, divided by all orders leaving the system. So we are interested in the items which are meeting the customer needs in terms of not violating the due dates divided by all orders which have been left in the FGI. So this is step 2 of the manual simulation.